So hello everyone. So today I'm very happy to present my work, Bayesian Design Principles for Frequentist Sequential Learning, which is a joint work with Assaf Zeevi. And in the first part of this talk, I would like to talk about the motivation and contributions. So in this work, we study sequential learning with partial feedback, when an agent sequentially makes decisions to maximize the cumulative reward. So here, the challenge is that the agent will only observe the feedback of her chosen decisions, but she will not generally observe what the feedback would be if she had chosen another decision. So there is trade-off between exploration and exploitation. That is, the agent needs to try different decisions to learn the environment, which is exploration, and she wants to focus on good decisions and avoid bad decisions to maximize the incurred reward, which is exploitation. This exploitation trade-off arises in all the sequential learning problems. And in this work, we develop a very general theory encompassing binary problems, reinforcement learning, and beyond. Let me introduce one of the most fundamental problems of sequential learning, the multi-R binary problem with the Bernoulli reward. So here, as you can see, there are 4 machines. Each machine has a reward 1 or 0, and the probability is unknown to the agent. And at each time, the agent is required to pick a machine to maximize the cumulative reward. Here, the central challenge is that the agent will only observe the reward 1 or 0 of the picked machine, but she will not observe the reward of other unpicked machines. Another important example is reinforcement learning, where the reward is state-dependent rather than being stateless, as in the earlier multi-R binary example. So here, the agent only observes the states insofar as the chosen actions are concerned, but the underlying state transition dynamics are unknown to the agent. So the agent needs to explore different states to learn the dynamics. So let me conclude the 2 traditional approaches to address the exploration-exploitation trade-off in sequential learning, frequentist and Bayesian. One of the most famous algorithms for the frequentist approach is upper confidence bound, the UCB algorithm. Here, the agent uses sample average or linear regression to estimate the mean reward, and she optimizes the upper confidence bound of the mean reward to make decisions. So as you can see, there are 4 machines, and for machine 2, 71% is the sample average estimate of the reward, and this 5% is the radius of confidence bound. So if we plus this 5% to the 71%, that's the upper confidence bound. By choosing the machine that has the maximal upper confidence bound, we encourage the agent to explore machines that are seldomly chosen in previous round. So that's the idea behind the UCB algorithm. One of the most famous example of the Bayesian approach is the Thompson sampling algorithm with a fixed pre-specified prior. So here, we update the Bayesian posterior at each round, and the agent will use the results from that posterior to make decisions. Here, the central idea is that instead of using point estimates, we will maintain distributions to estimate the reward and use these distributions to make decisions. I want to mention that neither UCB nor Thompson sampling is applicable to adversarial environment, and we will go back to this issue later. So let me conclude the salient characteristics of the frequency and Bayesian approaches. The advantage of the frequency approach is that it does not require the knowledge of the environment. For example, it does not require any prior of the environment. However, the drawback is that popular algorithms such as the UCB algorithm and exponential weight algorithm rely heavily on the case-by-case design and spatial structure of the problem. For example, we need to rely on the discrete or linear structure of the reward function to design efficient estimators. Without these structural assumptions, we do not know what's the estimator, and we cannot say what the algorithm will be like. The main advantage of the Bayesian algorithm is that the idea to update posterior is very general, precise, and interpretable if the prior is known. However, the main drawback is that it requires strong knowledge of the environment through a good prior, and this prior may not be accessible in complex settings. For example, if the environment is adversarial, then because the environment changes from round to round, so there may not exist a good prior at all. Also, maintaining the posterior may be computationally expensive. To sum up, the frequent approach requires less information, but it's more bottom-up. The Bayesian approach, on the other hand, is more top-down, but it requires stronger structural assumptions. So in this paper, we ask this main research question: can we develop principled Bayesian-type algorithms that are prior-free, computationally efficient, and work well in both stochastic and adversarial and non-situational environments? So this is a very ambitious question because basically we want to combine the advantages of the Bayesian algorithm, which is that it is very principled and interpretable, and the advantages of the frequent algorithm, that is, it does not rely on any information of the environment. And the main contribution of our work is that we developed an optimization approach that creates algorithmic belief at every round to simulate the worst-case environment and use the posteriors to make decisions. And in this way, we synergize the frequentist and the Bayesian approaches. So this idea is actually very simple. So you can even explain this idea to your grandpa and grandma. So what happens if the environment changes from day to day? The answer is very simple. You can just adjust your belief. You create a new belief every day and use the posterior of this new belief to make decisions. Yes, this is the very simple and short answer to this challenging question. But then there are a lot of questions arise. For example, what's the objective function to optimize? And I will answer these questions in the later talk. Because we create algorithm belief on the fly at each round rather than using a pre-specified fixed prior, so our algorithm automatically adapts to the adversarial environment. So this is intuition why we can achieve the very good performance in all the environments. And in this way, we developed the first Bayesian type algorithm that operate without prior assumptions and be applicable to adversarial settings. Also, because we use Bayesian postulates for random estimates and decision making, so this is actually more principled and precise than existing frequency algorithms. Finally, this algorithm is different than most existing algorithms because we combine the process to optimize for belief and decisions. This is like in contrast to most existing algorithms, which separates the black box estimation oracle and the separation decision rules. So at a conceptual level, the purpose of this work is really to develop some physical principles to design bandit algorithms and reinforcement learning algorithms. So just like solving the variational problem in Hamilton mechanics give you the laws of motion, solving our optimization problems automatically give you the optimal and efficient learning rules. And we illustrate our advantages in many applications. So one of our major applications is the multi-R bandit problems. For adversarial multi-R bandit problems, the exponential weight algorithm is the by default algorithm for decades, but we are able to develop a new algorithm called adaptive posterior damping, which is very different than exponential weight, and it's in closed form. And this new closed form algorithm achieves the best of our world empirical performance in our experiments in stochastic, adversarial, and non-stationary environments. We also have new theoretical guarantees for adversarial linear bandits, bandit convolutional optimization, and reinforcement learning, and many of the guarantees are state of the art. So now let me use one example experiment to illustrate the advantage of our algorithm. So here we consider 4-arm bandit problems where the mean reward of each arm is a sine curve as shown in the left figure. So I think this is a very good example to show the fragility of Thompson sampling. So while commonly known as one of the best performing algorithms for stationary problems, for these non-stationary problems, Thompson sampling, the blue curve, is actually the worst performing algorithm. In contrast, our algorithm, adaptive posterior damping, achieves the best performance. And in these two figures, we track the selected arms and best arms throughout the process. So you can say the blue curve, the blue points are the optimal arms at each round, and the red points are the arms selected by our adaptive posterior damping algorithm, and the blue points are the arms selected by the posterior damping algorithm. So as you can say, our algorithm is highly responsive to the changes in the best arm, while the blue points, the Thompson sampling algorithm, is relatively sluggish in this regard. So I think that this experiment shows that the idea to create a new algorithm belief, it has the potential to be a game changer in a lot of natural environments. For example, this sine curve environment, you can naturally imagine this sine curve to be corresponding to some signal chain. So these equations have a lot of mapping in practical applications. And in many applications, we believe that this simple idea to create new beliefs at each round have the potential to be a game changer. Okay, so in the second part of the talk, I would like to introduce the framework and the algorithms. So in our framework, each problem instance includes the decision space pi and the model space M. And each model M is a mapping from decisions to distribution over observations. So, and we denote the mean reward function for model M as Fm. Here is an example. In the Bernoulli multi-bandy example, the decision space is a finite set of k actions. And if we have a parametric set theta, which is the set of mean reward, then the model class can be indexed by the parameter space. So each model M is parameterized by the parameter theta, where the model M theta is a mapping from decision space to the Bernoulli distributions with the mean reward vector. And the mean reward function will be the mean reward factor itself. So this is how we cast our general framework into this special multi-bandy problem. And we consider as the adversarial environment, which at each round, the agent selects the decision probability, then the environment selects the model MT, and then the agent will make decisions and receive the observations. And the regret is defined as the difference between the best possible reward and the cumulative incurred reward, where the benchmark pi star is the best single decision in hindsight. So this best single decision in hindsight may change every round in the adversarial environment. But in the stochastic environments, because all the model MT will be the ground truth model M star, so the best single decision pi star will be the natural oracle that minimizes the mean reward function. So now, please take. So now, me introduce our main algorithm, adaptive posterior damping algorithm. So you must be very curious how this simple idea gives rise to actually a very elegant theory for very general cases. So we began with the uniform distribution among the decision space, so we do not require any prior knowledge of the environment. And at each round, we find a distribution nu t, which is a joint distribution of the model and the optimal decision, and this solves some optimization problems and give some algorithmic prior. Then we sample the decision and observe the feedback. Now, because we have the prior nu t, and we also have the observation pi t and ot, we can use the Bayesian rule to calculate the posterior belief of the model and optimization. And we always use the posterior, marginal posterior belief to make decisions. So the main difference between our new APS algorithm and the traditional Thompson algorithm is that we always create a new algorithm belief at each round and use the posterior to make decisions. But in traditional Thompson sampling, it will directly use the last round posterior as the belief of the current round. So our algorithm creates a new algorithm belief, while Thompson sampling only uses the last round posterior as a new belief. So this is the main difference in their idea. So, and the algorithm belief nu t will serve as a random estimator of the model MT and the optimal decision. And by optimizing the objective function, we are simulating the worst case environments. So now this is the important part. So what's the objective function? And this is the magic of how this simple idea can lead to a lot of efficient algorithms. So here, we propose an intrinsic compacting measure called algorithmic information ratio. So we believe this algorithmic information ratio is like the Hamiltonian for the interactive sequential learning problems, because it serves both, it will appear in both upper and lower bounds, and optimize this objective function will automatically give you closed form solution for many important sequential learning problems. So this algorithmic information ratio consists of 3 parts. The first part, the purple part, is the expectation of regret, where the model and optimal decision is drawn from the prior, and the decision is drawn from P. So this part corresponds to exploitation. The second part, which is the information gain, is the carrier divergence between the posterior and the prior. So this measures how much information you can get after you get the observation. So this part corresponds to exploration. And the last part is the regularization part, which forces the new belief to be close to last from the posterior. So again, let's remind that in Thompson sampling, you only have the last term. So in Thompson sampling, you force the new belief to be identical to the posterior of the last round. So basically, Thompson sampling is that you only have the last term, and that forces your new belief to be identical to the last round posterior. But in our algorithm design, we have 3 terms, and the first term corresponds to exploitation, the second term corresponds to exploration. So by optimizing this new objective function, you automatically balance exploitation, and also make your new belief to be close to last round posterior. And by optimizing this objective, we also want the effective regret to be large. That means that the exploitation to be hard, and the information gain to be small. That means the exploration to be hard. So this is really that you want to simultaneously simulating the worst case environment while making your new belief to be close to previous updates. And because we can somehow show that the summation of the information gain and regularization term is bounded by a potential term, so we can show that the regret of any algorithm for any problem can be bounded by this potential term and the summation of the algorithmic information ratio. And this bound is always smaller than the traditional bound for Bayesian Thompson sampling. And this recovers the optimal regret bound for many classical instances such as KR bandits and D-dimensional linear bandits. And the main takeaway is that the regret bound of our new algorithm is no worse than the regret bound for the Bayesian algorithm. But we do not require any knowledge over prior, and this is applicable to the adversarial environment. So this is like a free range. So this is like a free range common true because you do not require any knowledge of the environment, but the theoretical guarantee is no worse than previous guarantees that know the environment assumptions. And also because this algorithm information ratio have close relationship to the intrinsic complexity of the learning problems, it will appear both in the upper and lower bound in the problems. And by optimizing this quantity, we can automatically derive optimal and efficient learning rules. I also want to mention that this algorithmic idea is very different to previous algorithm, because previous algorithm is often that, for example, in UCB and in Thompson sampling, you have a black box oracle, and you also have some optimization rules. But in our algorithm, it's you simultaneously optimize all the stuff. So this is more precise in many problems. Okay, so let me conclude. So in this work, we propose an optimization approach to generate new algorithm beliefs at every round and use the posterior to make decisions. And this gives us many theoretical findings for bandits and reinforcement learning and achieve best of hours empirical performance for multi-R bandit problems in our experiments. Okay, so thank you for listening to the talk. And this is the QR code for our archive paper.